Hello, I'm Ben, and this is Lab 2 Charge Tapes Revisited for Physics 2. The purpose of this lab was to once again use the charged pieces of tape to demonstrate the behavior of charged objects and to find the amount of charge in the tape, but this time we're using a more sophisticated model of how the tapes behave using a line of charge rather than a point of charge. The fundamentals of this lab include the more sophisticated model that we're using, where each tape is now represented as a line of charge with many discrete point charges that make up the tape, with each point charge carrying the same amount of charge, rather than simply one point charge as the whole tape. We're also still using Newton's second law, Coulomb's law, and the Coulomb constant in order to find the forces acting on these tapes, similar to as we did in Lab 1. The main finding of this lab was that using our new model, the charge was 1.355 times 10 to the negative 8 coulombs rather than 4.174 times 10 to the negative 9 coulombs. The main assumption in this model was that each tape had an equal amount of charge, and this charge is distributed across the length equally. We had more assumptions in the previous lab, but this one we stripped some of those assumptions away so we could get a more accurate calculation in the end. The physics ideas are still mostly the same. We're still using Coulomb's law, we're still using Newton's second law, and we're using gravity, but now we're also using the superposition principle, where this describes the idea that in order to find the total or net force on an object, such as a charged particle, you just add up all the individual forces that are acting on that particle using a vector sum. So this is a simple version of a free body diagram that is much more akin to what we did in this lab rather than the point charge setup from Lab 1, where we're still using the Coulomb force and gravity. The system is still the top tape, and the surroundings is still the bottom tape and the Earth. This time, each particle in the top tape has multiple Coulomb forces acting on it from each of the other charges from the bottom tape. So the experiment details are pretty much the same as they were before. We measure everything the same. Everything's the same. We're using the same data. The only difference is that this time we're using a different computational model, which is the line charge model, rather than the point charge model. So for this model, our initial conditions were Coulomb constant. Acceleration due to gravity is 9.81 meters per second squared because we are on Earth. The mass of the tape is this, and I was using n equals 250 for the number of particles, as this was what I found caused the forces to converge. So this model represents the tape as a line of charge that's made up of discrete charged particles, and this model calculates the electric force on each particle in the top tape caused by each particle in the bottom tape, as you can see on the right here. Then this model calculates the force of gravity on the top tape, and then it also adds up all those electric forces together to find the net electric force, as you can see in the bottom. The top right is just initializing everything, both the definition for the electric field and defining the line charges. And then in the bottom right, we have the actual calculations for finding each of the forces on the point charges, on the individual discrete charges. And then in the bottom, we're just adding everything up. So this is the output. This is the picture that we get, where you have all of these arrows that are representing the force on each individual particle, and then we just have our total forces here in the middle. We use guess and check to find the net charge on the tape, which was 1.355 times 10 to the negative 8 coulombs. And then this model is a lot more accurate than the previous one, since it had fewer assumptions. And this model follows from the data seen before, so any errors in the model predictions would be due to either an error in the data collection or an error in our assumptions in the creation of this model. This model uses the data from the previous lab, so everything should follow from there. Sources of error: we could have measurement error, just as we could before. We could also have an assumption fail, which would be that the tapes might not have equal charge, or they might not be equal, the charge might not be equally distributed, and our model could be imprecise. We're using 250 particles, but the actual number would be far, far greater than that. So if we model as a point charge, we would get the value I said before, and we got 1.355 times 10 to the negative 8 instead, and this is a this is 3.24 times larger than the charge calculated for the point charge model. And these estimates differ because the line charge model is taking into account many more interactions. And not all these interactions are directed directly upwards, so you're going to need a lot more charge. And the line charge model is a lot closer than the actual value. And then as a result of this, we got this value instead of this value, and the line charge is going to be a lot better than the point charge.